So today we are seeing chemical equilibrium. Chemical reaction don't go to completion 100% products. Even those that look like they do reactions inside reach a point called equilibrium. After these are like reversible reactions, after which the amount of reactants and products no longer change with time. This is because all the reactions are reversible. Okay, you can see here reaction here, N2O4 converts into NO2. This is colorless and this is brown, means the reaction goes in both direction, in forward as well as in reverse direction. Add some colorless N2O4 in an empty flash, then watch it in time. The gas will slowly go more and more brown as N2O4 converts to NO2, because this has brown color and this is colorless gas. You will see from colorless to brown. Okay, after a few minutes no further change colors. Okay, the reaction has reached the equilibrium and the gas contains both N2O4 and NO2, but that doesn't mean that they have in equal amount. Okay, just the amount of products, like you can say, like reached a point that they no longer change into each other. Okay, why doesn't it keep giving NO2 and going more brown? Because the rate at which N2O4 is giving more NO2 is now the same as the rate of reverse reaction. That's why it attains the equilibrium and there is no change in reactants into products. Okay, you can see in the diagram here, concentration of NO2 increases with time and concentration of N2O4 decreases with time. Okay, dynamic equilibrium is achieved. The rate of forward reaction and rate of reverse reaction are equal to each other. Okay, this is for forward reaction and this is for reverse reaction. Okay, you can see we will find equilibrium constant for this reaction. We write forward up and divided by reverse. We will get this value. Okay, rate of forward and rate of reverse are equal, so by using this we will get equilibrium constant for this reaction. Okay, equilibrium constant, no units, depends on the relative amounts of products and reactant at equilibrium. Only temperature can change the value of equilibrium constant. Reactants are defined as the things on the left and products as the on the right hand side. This is like basic thing. If value of K is large, it means the products are more. Products means NO2, like we are discussing in the previous section. NO2 reactants are more. You can say products are more, the value of K will be large. If products are less, or we mean that the reactants are more and products are less, it means the value of K is very small. And if both have like same concentration, then the value of K will be like, you can say, is equal to 1, because it is a ratio of reactants, products and reactants. If K is very small, we can say that there is no reaction. If K is very large, we can say that reaction has gone to completion, not 100%. Okay, chemical reaction never go exactly 0% or 100%. They are always equilibrium. This is intermediate K, this is large value of K, this is small value of K. Okay, you can see. Okay, reaction quotient, okay, represented by Q. This is reaction quotient. Okay, Q is the reaction quotient of mass action expression. As the reaction proceeds, Q is changing. When the reaction reaches equilibrium, Q is equal to K. Okay, here example here, find the value of QC. It will be like this. Products are on the top and reactants are below the equation. Okay, this is an equation, CH3H8. This is a reaction. This is not balanced. Okay, because here are 3 carbons and here one. First balance this. Okay, different forms of Q and K. Q and K refers to the particle equation. If the equation is written different, Q and K changes. Okay, you can see here are like 2 moles of SO2 and here are 2 moles of SO3. So the equation will be different for both. Okay, for more than one step reactions, you use these equations, okay, multiply by both of them, then you will get your answer. Okay, yeah, uh, this is ideal gas equation. PV is equal to nRT. Total pressure is found by adding all the pressures. Okay, Pi is the partial pressure of gas. You can use this equation for pressure constant. Okay, quotient. Okay, like previously we were discussing about equilibrium constants, and here expressed as pressures. Okay, QP and KP. There is a reaction here. You can write this equation, relation between Kp and Kc. Okay, Kp is equal to Kc RT into delta N. Predicting direction of reaction. If K is more, products are favored to the right side. Like products favored, equilibrium moves to the right side, onto the product side. Okay, if K is small, like you can see, is like smaller than 0.1, reactants are favored and the equilibrium moves to the left. If K is like normal, the both reactions are products in significant amounts. If Q doesn't equal K, reaction is not in equilibrium. Net reaction will occur until equilibrium is reached. If Q is greater than K, reaction proceeds from right to left in the backward direction. If K is greater than Q, the reaction proceeds from left to right in the forward direction, and when Q is equal to K, reaction at equilibrium, no change of concentration occurs. Example here, okay, you can see this. This is write down in your notes, so when you are revising these topics, so you can get quick revision. Okay, here's a question: how a 2-liter flask is filled with 0.2 mole of HI and allowed to reach at equilibrium. At equilibrium, HI is this. Calculate Kc. We're given this 0.1 molar of HI. Okay, 0.1 molar of HI initial. Okay, so I think, okay, 2 moles here, so we have 0.2 molar. Okay, at start, S2 and I2 have 0 concentration, change is minus 2x, so we minus this 100 minus 2x, then we will get x values of S2 and I2. By initial concentration of HI, we will find that is 0.100 molar. Okay, this is molar. Moles are this. We find out moles by this equation. C is equal to concentration by this. C is equal to N by V. Okay, V is 2 liters and this is 0.2 mole, so we will get 0.100 molar concentration of HI. Okay, by writing this, we minus 2x, this is okay, minus 2x, we have concentration of this, we divide minus 2x, we will get 0.01 moles. Okay, or we will write like same value. Okay, Kc is calculated. Alright, write values here. Okay, then we will get 0.02, the value of Kc. Okay, another question here, you can see the calculations. Alright, if you have any concern in this, let me know. Yeah, using the quadratic formula to find, sometimes we are unable to find the value of x by other methods, so we apply quadratic formula to find the value of x in this type of questions. Okay, Le Chatelier principle. If a system of equilibrium is disturbed, it will then adjust in a way that reduces the effect of disturbance and returns to equilibrium. If A plus B is the reactants and it converts into C plus D, the equation for Kc will be written like this. Okay, If concentration of D increases, the reaction moves to left, okay, and if concentration of D decreases, the reaction moves to right, okay. The reaction does what is necessary to recover from the disturbance and restore. If you can say we have added more AR more, so reaction will move in the forward direction so that the equilibrium is attained, okay. Effect of change in concentration. To predict how will it respond, consider how Kc is affected by disturbance compared to Qc, okay. Any of these changes cause a shift. If we increase this PCl3, the reaction moves forward. If we increase this, the reaction moves forward. If we decrease this, the reaction moves forward, okay. And if we decrease, the reaction moves reverse. And if we decrease this, the reaction moves reverse. And if we increase this one, the reaction also moves backward, okay. Some questions here, okay. When Qc is greater than Kc, change in pressure, okay. Change in pressure of one gas involved in the reaction depends, okay. This doesn't change Kp. Addition of inert gas not involved in the reaction, the total pressure P increases, but the partial pressure of the gas involved in the reaction stay the same. No change to the equilibrium in any way because Q is equal to K still. Change in the volume of the vessel, this changes the total pressure. The partial pressure of the gas involved in the reaction also change. The reaction proceeds in the direction that opposes it. Like if one side volume increases, like product side, the reaction moves the other side, okay. Only if the equilibrium has been disturbed, okay. Qp is equal to not equal to Kp. Reactions here you can see N2 plus 3H2 P increased in the following reactions, then you can say reaction proceeds from left to right, okay. When pressure is increased, it moves towards that direction with lesser number of moles. You can see here 4 moles of reactants, 2 moles of product, so the reaction will move towards the right side. Here you can see pressure is increased, the reaction moves from right to left in the backward direction in that side where number of moles are lower, and here number of moles are same, so pressure will not affect this reaction, okay. You can see if the number of moles on the two sides of the reaction is the same, changing the volume has no effect on the equilibrium. You can see effect of pressure, okay. Some problems here predicting the effect of change in volume pressure on these reactions. I give you knowledge about this. Try to solve these questions. Change in temperature, how change in temperature affect equilibrium, okay. And if for endothermic reaction, if temperature is increased for endothermic reactions, if temperature is increased, then it will move from left to right. Left to right means in the forward direction, and the value of K will increase. You can see here value of K will increase for endothermic reactions. When temperature is decreased, the reaction will move in the left side from right to left. The value of K will decrease, okay. For exothermic reactions, when temperature is decreased, it is reverse of you can say if reverse of endothermic. You can see when endothermic temperature is decreased, it moves from right to left, but here when exothermic reaction is decreased, it moves from left to right. It is totally opposite. So what is the relation of temperature with the endothermic reaction? Reverse. You can say for exothermic it will be reverse, okay. And for when we increase temperature in exothermic, the reaction will move from right to left and K will decrease. Think of heat as a component of the reaction. Endothermic, A plus heat B, temperature increases, heat increases, reaction shifted from left to right, K increases, okay. In exothermic, heat is released, but in endothermic heat is added. So for exothermic, when heat is released, temperature increases, heat increases, reaction moves from right to left, and K gets smaller, okay. Van Hoff equation here, you can see here This tells us how K changes from K1 to K2 on going from T1 to T2. The change K with T depends only on the delta H naught, okay, of the reaction. The amount of equation looks similar to the Arrhenius equation for the change in the rate constant K of a reaction as T is changed. Okay, these are like answers. When questions here, when increase in temperature, what will have effect, what is the effect, where the reaction will move. You can see this is exothermic, this is endothermic. Okay, you can use your knowledge to solve this. Answers are given here. Okay, addition of a catalyst only speed up the rate of the reaction but does not change K. Affect the equilibrium, doesn't affect the equilibrium constant. A catalyst will speed up the reaction at which rate it reaches equilibrium. Doesn't affect the equilibrium position. Okay, it acts for both forward and reverse reaction. The rates of reaction affected by the activation energy barrier that must be overcome for the reaction to occur. We said that rates of reaction involves kinetics. The equilibrium constant is not affected by activation energy barriers. It depends instead of thermodynamic quantities such as enthalpy and that we study in thermodynamics. Okay, chemical kinetics. Okay. Okay. Let us repeat one more. The only change that will alter the value of K is to change the temperature. The other changes can affect the relative concentration or pressure of the reactants and products, but they do not change the value of K. Alright. Okay, you can see here the what we studied. This is the whole summary: concentration effect, pressures effect, temperature effect, and catalyst effect. Okay. So good luck. I hope you enjoyed the lecture.